Hello, just doing a quick video because Ksenia asked me this question in class. Apologies for the sound, like you might hear some harmonica being played by a 2-year-old in the background. But yeah, okay, so I'm going to take you through this question. I want to do the first part anyway. Sorry, this is a bit loud. Yes, Bibsy. Yes. She's just going to play lots of harmonica. But I reckon I can explain this even with her bugging me right next door. Okay, so here goes. What we've got here is, now, the way we're going to do this is we're going to appreciate that, like, when you're going from yn to yn plus 1, yeah, what's really happening? Well, you're firstly going from, like, a certain x value to an x value plus a step length of h, aren't you? Yeah. So in other words, to go from yn to yn plus 1, we're going from f of x to f of x plus h. Yeah, that's what we're really doing. So if we can interpret these, yes, all right, Bibsy. What we're actually doing here, if we're going from here to here, then yn going back to yn minus 1. That's where we're actually going from x to x minus h, yeah? And so f of x is going to become f of x minus h, yeah? So what I'm going to do to prove this first result is I'm simply going to, I'm not really proving a result because I'm justifying an approximation really using Taylor expansions. Now recall that Taylor expansions at 0, which is what we've got here, in other words the Maclaurin expansion, is that f of x equals f of 0 plus x times f dash of 0 plus x squared over 2 factorial times by f double dash of 0, and so on and so forth. Yeah. It might also be worth pointing out that if you just take the first few terms of this expansion, you get a good approximation, and that's what we're going to do here. We're just going to look at the first few terms to get a good approximation. Okay, so let's do that. Okay, so we already know that for our specific case, where we've got d2y by dx squared equals x plus y plus 2, subject to the boundary conditions that when x is 0, y is 0, and when x is 0, dy by dx is 1, we can therefore work out what f of x roughly equals. So in our case, f of x is equal to f of 0, which we know is 0, plus x times f dash of 0, which is x times 1. Yeah. Now, we can also work out f double dash of 0 if we plug these two ideas in here, because we can see that the second derivative equals x plus y plus 2. So in other words, f double dash of when x is 0, we know when x is 0, y is 0, we're going to get f double dash of 0 equals 2 here. So we can use that situation as well. So we're going to be putting in here x squared over 2 times by 2. Yeah, plus dot dot dot. So I know that f of x, at least at x equals 0, that roughly equals x plus x squared. Yeah, plus dot dot dot. Yeah, well, it exactly equals a dot dot dot, but let's just say it roughly equals x plus x squared. And so I now know how to find f dash of x. It's going to be roughly equal to 1 plus 2x. Yeah. So what I'm going to do is I'm going to take the right hand side of this first result I'm trying to prove. Let's put it in highlighted. Yeah, I'm going to try and prove this. Just this one first. Yeah. Let's clear it up a bit. Good. My children have gone now, and I can actually do this without the noise. Oh, I've done it again. I'm going to try and prove this result, yeah? And I'm going to use these ideas that, like, I'm going a little bit above and a little bit below. You know, I'm doing x plus h and x minus h for yn plus 1 and yn minus 1. Well, I can see, therefore, that the right-hand side, and I'm just looking at star here, will do, if we call this diamond, we'll do diamond maybe afterwards. I strongly suggest, though, have a go at the second one on your own, because you might be able to do that once you've seen me do the first one. Okay, I'm going to do yn plus 1 minus yn minus 1 over 2h, yeah? Well, that's going to be equal to... okay, what is yn plus 1? Well, it's when we've got f of x becoming f of x plus h. So I'm just going to replace, in my expansion, f of x, yeah, I'm going to replace it with x plus h. So I've got f of 0 plus x plus h times by f dash of 0. Now remember, I already know what f dash of 0 is. It is 1 plus x plus h all squared over 2 factorial multiplied by f double dash of 0, which I know is 2, so that's going to cancel with that, yeah? Minus, that's just this one I've done there, yeah? Minus ym plus 1, which is going to be f of 0 minus x minus h, but the coefficient's going to remain the same because it's still f dash of 0 is 1, minus x minus h squared over 2 factorial times 2, yeah? All of that on the top and just 2h on the bottom, yeah? Now let's see what this goes to. Obviously the f of 0's cancel. Now the x minus x cancels, but we will have h minus minus h, so that's going to give us 2h. And then for these, think about what it's going to expand out to give. You're going to have x squared plus 2xh plus h squared, but then you're going to be doing minus, in brackets, x squared minus 2xh plus h squared. Now what's cancelling here is a lot of stuff. The x squareds are going to cancel, the h squareds are going to cancel, and we're going to be left with the following. 2h plus 4xh in total after you've added that all over 2h. Now what does this come to? This comes to 1 plus 2x, yeah? And that is exactly what we thought what the derivative was approximately equal to, yeah? And so this must equal, like, the derivative. Yeah, remember as well, what is this? What we're doing here is we're doing the case of dy by dx at n, because at n we said basically we're at x, yeah? And so n is the case where we're going to be at x, and so we're just plugging in x, not x plus h. And so, if you like, maybe I should have used different notation there. This is dy by dx at n, yeah? And this is because this is f of x, well, y at n. I should have made that clear earlier, sorry. Yeah, because I'm just using x here, not x plus h. And so I can now say, and this equals, or roughly equals, dy by dx at n. Yeah? Okay, I suggest you pause the video now and have a go at proving the secondary result yourself. Hopefully you've paused it. Now I'm going to have a go at proving it. I haven't proved this one yet, so it'll be interesting for me to do. Okay, let's have a go at it. What we got here? Well, similar kind of strategy. I've already worked out what ym plus 1 is, what ym minus 1 is, and yn, remember, is just this. So I can easily, do all of that and see if it equals the left-hand side. But what is the left-hand side? Well, d2y by dx squared at n is just going to be the derivative of this, yeah? So d2y by dx squared at n is roughly equal to 2, yeah? Okay, so hopefully, if I investigate the right-hand side, it should end up equaling 2. Let's see. Okay, right-hand side. Right-hand side, what is that equal to? Well, we've got exactly what we had before, but it's a plus here, and then we've got minus 2 lots of these, yeah? So, let's have a look. I've got, now if I remember rightly, I would have had x plus h, I think it was x plus h, that's where it started, wasn't it? X plus h, oh, f of 0, I should include the f of 0, because you never know, it might play a role. Oh, f of 0 though is simply 0, isn't it? So I can ignore the f of 0 safely. So x plus h squared plus x minus h plus x minus h squared, that's essentially what I've got. X plus h plus x plus h squared. I'll leave the minus 2, and then I'm going to have plus x minus h plus x minus h all squared. This is all over h squared, remember. Now what was that middle term? It's 2yn, and yn is this, so it's minus 2x squared. Minus x plus x squared goes in there, yeah? Now hopefully this is going to go down to 2, yeah, that's what I'm hoping for, and then that will justify that the Euler approximation formulae do actually pop out of the Taylor approximations, basically, if you use step lengths of x plus h and x minus h. Okay, so what have we got here? We've got, if we just do it like this, what's going to cancel? The h's are going to cancel, the h squareds, let's be careful. Yeah, they're not going to cancel. We're going to have x plus x, which is 2x, but minus 2x, they disappear, yeah? And then what you're going to be left with on the top here is you're going to have an x squared plus 2hx plus h squared minus 2x squared I've already dealt with a minus 2x, plus x squared minus 2hx plus h squared, yeah, all over h squared. Now the x squareds are cancelling with a minus 2x squared, the 2hx is cancelling with a minus 2hx, we've got 2h squared over h squared, which equals 2, which roughly equals, we can say, the second derivative at n. And that concludes the proof, or the justification. I'd love you. I don't know where you got this question from in Mad as Maths, and I'm not really massively fussed about hunting it down. This is essentially the idea I'm pretty sure that they'll use. Could you let me know if they use a radically different approach and ask me to take a look at it if it looks really different from my approach, and let me know if my approach makes sense. You might be wondering why I can just truncate the Taylor approximations. I hope you realise, I can easily explain that to you in class, I hope you realise that Taylor approximations around a certain value, basically as you use more and more terms, it's only affecting like later and later significant figures, the fourth significant figure, fifth significant figure, sixth significant figure, and so we can get away with it. But yeah, ask me in class if you're still confused and let me know if it made sense. All the best, bye bye.